Welcome to this lecture series in linear algebra. In this lecture, we'll learn a very nice decomposition theorem applicable to any endomorphism. And all we need to know basically is what is meant by a direct sum. Of course, we need to know more things, but let me just recall what's the meaning of this. So when we have a vector space V and we have two subspaces U and W, we write this to mean that, first of all, this happens, which means that any vector in V can be written as the sum of a vector in U and a vector in W, and uniquely so. So not just that this is the case, but that for each vector V, there is a unique element in U and a unique element in W such that this happens. But it turns out that this is equivalent to saying that this is the case. So writing this is same as that, even though the definition is not quite this. Definition is a little bit different, a more meaningful one, but it is equivalent to saying this. All right, so I'm sure you recall this. And now let us move on. Here are some problems for practice. And now let us get started. So we'll recall a bit of notation. If we have an endomorphism on a vector space V, then recall that we write this t to the power 0 to mean the identity map. This is a convention. This we write to mean t composed with t, and in pictures you can express it this way. So that's one way to depict t square or t to the power 2. Similarly, we have t to the power 3. And so on. So we have these things, and note that kernel t is contained in kernel t square, is contained in kernel t cube, and so on. Very simple observation. Okay, and now we have something which I like to call the kernel saturation lemma. It says that if T is an endomorphism on a vector space V, again, everything is finite dimensional, and we have a positive integer k such that we do not see an increment in the kernel. Even though we have this chain of containment, suppose at some point we do not see the chain growing, then the theorem says that we will not see the chain growing from that point on. The chain will stabilize. It will saturate, so to say. Okay, so let's prove this. It's a very, very simple proof. So what we will show is this is the case. Once we do this, then we have shown this part, and then you can continue the reasoning to include all the other higher powers. So let's just be content with this much. So what we have is, so fix some vector in this guy arbitrarily, and enough to show that, or we want to show that, right? So this will, once we show the orange thing, it will show that this guy is contained there, but the reverse containment is already present, so that will show the required equality. All right, so what we have is, this is 0 simply because V is in the kernel of t to the k plus 2, which implies that therefore TV is in the kernel of t to the k plus 1. But kernel of t to the k plus 1 is kernel of t to the k by hypothesis. So therefore this lies there, and hence this is the case. Therefore we have that. which is same as saying v is in the kernel of t to the k plus 1. But once again, kernel of t to the k plus 1 is kernel t to the k by hypothesis, and therefore we are done. This shows the orange thing and we are done. Okay. So an immediate corollary of the kernel saturation lemma is the following. If we have an n-dimensional vector space and we have an endomorphism T on it, then kernel of T to the n, this is the dimension, is same as kernel of T to the n plus 1, is same as kernel of T to the n plus 2, and so on. So why is this? So here is the proof. If there is some k such that this happens, then immediately this happens, immediately by the kernel saturation lemma. So then clear by KST or KSL, kernel saturation lemma or theorem, whichever you want to call it. So we may assume otherwise. So otherwise, consider this chain. We have this chain, and by our assumption, meaning such a k does not exist, this containment must be strict. This must be strict. Each containment must be strict. So we slash out the equal to sign. So this must be the case, and therefore this has to be a non-trivial subspace. Because if this were the trivial subspace, that would mean T is injective, and hence T would be an isomorphism. Recall, if you have an endomorphism which is injective, it is automatically an isomorphism by the rank nullity theorem. So if this were the trivial subspace, T would be an isomorphism, and hence this would be an isomorphism, and hence each of them would be the trivial subspace, and therefore these containments wouldn't be strict. So this is a non-trivial subspace, has dimension at least 1. By the strict containment, this should have dimension at least 2. Again, dimension at least 3, and so on, and this must have dimension therefore at least n. But the dimension of this cannot be more than n, and therefore this must then be the entire vector space V. Now if this is the entire vector space V, of course each subsequent thing in the chain is also the entire vector space V, and then this holds trivially. So in this otherwise case, this is the argument which I said, and I don't want to write it down. And in the non-otherwise case, the statement is clear by the kernel saturation lemma. Okay, so now let us move on. So here is the decomposition theorem that we want to prove. Fix an n-dimensional vector space V and an endomorphism on it. Then the vector space can be decomposed in this fashion. Kernel of T to the n and image of T to the n form a direct sum decomposition of the vector space. And I have just expanded that out here, what that direct sum means. So here is the idea or proof. Again, it's a very simple proof. It will use the previous corollary. So define the endomorphism S as T to the n. We claim that so this claim is part of the direct sum statement. Okay, so pick something here arbitrarily. Towards this claim, let V be some arbitrary element in this intersection, and we will show that V is 0. So then, in particular, if V is in this intersection, then in particular it lies here, and therefore there is some vector u such that V is SU. Fine. Simply because V is in the image of S. Now use the fact that V is in the kernel of S. Therefore, 0 is equal to SV, because V is in the kernel of S, which is equal to that. But that is equal to this, which is equal to that. Sorry, this is a U. Okay, which implies that 0 is this thing, meaning U is in the kernel of T to the 2n, but kernel of T to the 2n is kernel of T to the n by what we saw in the previous slide. And therefore, T to the nu is 0, which implies Su is 0 because T to the n is S, which implies V is 0 because V is S of U. V is S of U. So V is 0, and that's it. So that proves this claim, and therefore we will be finished if we can show that the dimension of this plus dimension of that, or rather, okay, so fine. So what we want to show is that the dimension of, or rather, what we are interested in is kernel S plus image S. We want to show that this is the entire vector space V, and that can be done if we can just show that the dimension of this thing is n. But what is the dimension? The dimension of the sum is the sum of dimensions minus a correction term, right? So recall that dimension of U plus W is dimension U plus dimension W minus dimension U intersection W. This is generally true for any two subspaces. We also saw this as a consequence of the second isomorphism theorem. Alright, fine, but we have already shown that this is the trivial subspace, and hence we can erase this from this equation because that quantity is 0. So therefore we see that the dimension of the sum is the sum of dimensions. But now apply rank nullity theorem to the endomorphism S. To the endomorphism S, and by the rank nullity theorem, the dimension of the kernel plus the dimension of the image is the dimension of the parent space, which is n, and we are done. So we have shown both these things, and hence we have proven the direct sum statement. So that's a very nice proof of this decomposition theorem. Perhaps we will make use of it at some point. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.